Hi guys, how you doing? So let's see here. We are going to do 8.2, which is the entire chapter on estimating proportions with confidence and confidence intervals of proportions. And we're going to do concept 3. So let's take a look at that right now. 1 second. Here we go. Okay, so let's see here. All right, as noted in section 8.1, our goal is to estimate the parameter as precisely as possible. We want high confidence on a low margin of error. Okay, so we want high confidence on a low margin of error. And by the way, I wanted to explain that, remember, when we first talked about confidence intervals, what we have, right, is right here, we have a point estimate right here. And that's, in this case, it would be like your sample proportion, or it could be your sample mean. But right here, we have a point estimate, right? And all these confidence intervals. Right here, we have the positive margin of error. And right here, we have this is called the rightward and leftward margin of error, right? But each of these is a margin of error, and that makes up this whole thing right here we call a confidence interval. Okay? So just want to remind everybody about that. And then mathematically, how that was created is what? We have the point estimate plus or minus the test statistic times the standard error of the statistic. All right, so what does that mean? Okay, well, in this case, since we're doing proportions, so for proportions, we get that as we have the sample proportion, because we don't know the population proportion, so it would be the sample proportion plus or minus. The test statistic in this case is going to be Z star. And the standard error of the statistic, that's, remember, the same thing as the standard deviation of the sampling distribution of the sample mean, but we're just going to be using p hat this time. So that's just going to be, standard deviation of the sampling distribution of a sample proportion, but we're going to use right here p hat. So p hat times 1 minus p hat over n. So there it is. Okay, that's the formula. All right, so just want to remind everybody about that. So that's what you can see right here is if p hat is our point estimate right here, the positive margin error is just going to be, basically this right here is just going to account for p hat plus, right here, Z star times the standard error, which is, right, p hat, 1 minus p hat all over n. And this right here accounts for p hat minus Z star, which is the test statistic times the standard error, p hat times 1 minus p hat all over n, okay? So I just want to clear that up for everybody. So this entire right here from there to there is the confidence interval. All right, so let's do it. All right, so right here, as noted in 8.1, our goal is to estimate the parameters as precisely as possible. We want high confidence on a low margin of error. To achieve that, we can determine how large a sample size is necessary before proceeding with the data collection. To calculate the sample size necessary to achieve a set margin of error at a confidence level C, we simply solve the following inequality for n. Z star times the standard deviation of p hat times 1 minus p hat all over n is less than or equal to the margin of error, where the sample proportion is estimated based on a previous study or set to 0.5 to account for the maximum possible margin of error. And all these problems that I've seen, it's almost always you just substitute 0.5 for it. So let's take a look here. A researcher would like to estimate the proportion of adults who can roll their tongues. However, unlike the previous example, she'd like the margin of error to be at most 2%. Okay, so at most 2%, that means it has to be less than or equal to 0.02. Okay, so our margin of error is we want it to be 0.02 here at a 95% confidence level. Okay, so we're at a 95% confidence level. All right, very good. How large is a sample is needed? So we're going to use the formula for margin of error. That's going to be z star times p hat times 1 minus p hat all over n. So let's get everything that we need right here. Okay, first of all, z star. How do we get that? Well, we know that depends on what the confidence level is. This is 95% confidence level, so what we're going to do, just go ahead and draw a normal curve. 95% is all right there, 0.95. And we know that 100 minus 95 is 5, divided by 2 is 2.5. So that means that this is, remember, if I put that as a decimal, that's going to be 0.025, right? So it's going to be 0.025 here, 0.025 right there. Okay, so let's take a look right here. So we need to get the z star value. So we're going to use, of course, right here to get that. We'll just go and put inverse normal. The area is 0.025. The mean is 0. The standard deviation is 1. All right, we'll just go and put that into the calculator. So here we go. Second distribution, inverse normal. There we go. So 0.025. And then right here, paste. We got it. All right. And that gives us right there negative 1.96. So that means our z star value is just going to be 1.96. So what that's saying right there is that if you have a 95% confidence interval, the z star value would be 1.96. So this value right here is 1.96, and that value right there is negative 1.96, okay? Which makes sense. Remember, way back when we did the 6895 99.6 rule, we said it's about 2 standard deviations away from the mean. All right, and that's negative 1.96 is about a 2. All right, so we have this as 1.96. P hat. Now we said right here that P hat right here, if you look up here, is we use 0.5. Okay, and that gives us the maximum possible margin of error. Okay, so that's like a conservative estimate. So we'll say that in this case, we're going to say that P hat is going to equal 0.5. 1 minus 0.5 is still 0.5. Now we don't know the sample size. They ask how large a sample is needed. So n is going to stay n, and that's going to be less than or equal to the margin of error. So they want the margin of error to be 2%, so that's going to be 0.02. All right, there we have it. So there's our equation right there. All right, let's see if we can figure this out now. All right, so I'm just going to take this equation right here and just solve it. I'm going to write it over here if you don't mind. So that's going to be right here, 1.96 times 0.5 times 0.5 over n less than or equal to 0.02. There we go. All right, we're going to solve it. So what I would do, what you should do to get a most accurate n value is don't actually use your calculator to the very end. Just go ahead and solve first. So first I'm going to divide by 1.96 on both sides. So I have here the square root of 0.5 times 0.5 over n is less than or equal to 0.02 over 1.96. Then right here, I'm going to go ahead and square both sides to get rid of that radical, that square root. So that's gone right there. So I have right here 0.5 times 0.5 over n is less than or equal to 0.02 over 1.96 quantity squared. And then right here, I want to get n to the other side, so I'll multiply n on both sides. So that gives me 0.5 times 0.5 less than or equal to 0.02 over 1.96 squared times n. And of course, I'm solving for n right here. So if I'm solving for n, I'm just going to divide by this right here. Okay, there we go. So we're going to divide by this right here, 1.96 quantity squared. There we go. All right. So now I'm just going to use my calculator to figure out this will give us an accurate value. I mean, if you wanted to, you could have figured out 0.5 times 0.5 is, of course, 0.25. You could have put that there. It didn't matter. So let's do it right here. So I have right here 0.5 times 0.5 is going to be, of course, 0.25 divided by parentheses 0.02 over 1.96 right there, quantity squared, and there we go. So that gives me that 2,401. All right, so we have right here that 2,401 is less than or equal to n, so n must be at least 2,401. Okay, so your sample size, so n, which is my sample size, must be at least 2,401 to have the margin of error of at most 2%. Okay, is what they had asked right here. So specifically, they had said, sorry, let me go over here. Where did I go? Sorry, I've lost my place. There we go. So right here, how large a sample is needed to right here have a margin of error at most 2%. So the margin of error has to be right here at least 2,401. Okay, that's it. All right, so we'll talk a little bit more about this tomorrow when we meet, but that is it.